This class and the tutorial after this, we will be looking into what is called incidence geometry. Okay, so this will be some on a topic which is like a very simple, not hard. Not that the previous one was that hard, but this will deal with objects, simple objects. Okay, mostly points and lines in art, most cases. Okay, other thing that we will do is points and circles. But even with these very simple objects, you can do very interesting math. Okay. So, incidence geometry, there are like many different topics to cover. So, I just want to give a brief introduction on the topic first. Like first 10-15 minutes I will do that, and then from that I will cover one result properly through, and I will give you some interesting application of that result. Okay, that's the goal. Okay, so one classical problem to look at is what is called point line incidences. So, what is it about? Okay. So, what you have is, let us say you have some collection of points in R2. Okay, the point set, collection of points in R2. Okay, good. Let us say you have m points in R2 and you have a collection of lines. So, this is let us say m, this is let us say n. Okay, so, now what we want to understand is, so some lines, let me draw some lines. Okay. So, you can define what is called incidence pairs I of p comma l, which is equal to, so let us say call this this be p 1 dot dot dot, and let us say this be l 1 small l 1. Okay. So, it will be of the form small p I comma small l I pairs, such that small p I belongs to capital P I, L I belongs to capital L, and P I lies on L I. Let us say call it P J, L J. P I lies on L J. Okay. So, I am counting tuples of points and lines, okay, such that the point lies on the line. I am not considering all lines, I am restricting myself to lines in the set L and points to points in the set P. Okay. So, what we want to do is, the question is, estimate this object. This very innocent looking object, innocent looking problem has huge applications. So, by the way, we can keep still points, but if I replace lines with some other algebraic curves, let us say circles and stuff like that. Okay. These has applications in number of different places. So, one application I am telling you, which is an interesting thing is, so let me try to bring it down. So, let us go to new page. Okay. So, what we want to understand is, let us say you have another question, a set. So, let us say question 2. You have a set A in subset of a finite set in R2, in R, sorry. You can define A plus A is equal to all A plus B such that A comma B belongs to A. And similarly, you can define A dot A, which is equal to A B such that A comma B belong to A. This will be a set, right? Let us say I want to estimate this. Estimate size of A plus A dot A in terms of size of A. This is a very fundamental question in additive number theory. These are what are called additive structures. These are multiplicative structures. Okay. You can prove some interesting bounds. You can prove if you can show that if this size is small, then this size will be at least be of some size. If this size is small, then it will be of some size. You can have different relations between them. Okay. Sorry. What happened? Okay. Similarly, there is another question that okay, so let's see, this another question is a question in discrete geometry. So let's say let P be a set of n points in R2. Okay. Estimate number of unit area triangles that can be formed with vertices from P. So apparently this problem and the previous one doesn't look like the main thing that we wanted to study, ILP. Directly you don't see a relation, right? I mean, this is something to do with area, that is more of a linear object and incidence between lines and points. But we will see a connection in these two lectures. Okay. What are other examples that I wanted to cover? Okay, let's look at another problem. There are many others. I will just concentrate on these few. Another one is, let's say you have a very fine unit grid. Okay, a fine grid. Okay, infinite grid in R2. Okay, and you have a strictly convex curve in R2. So what is a strictly convex curve? So if I joint any 2 points on the curve by a segment, the interior of the segment should be completely inside the curve. Is it clear what I am saying? Is this strictly convex square? No. Okay. Strictly convex is what we are restricting. So you have some strictly convex curve here. You want to estimate number, so let's call this grid Z2. Okay. So the curve let's call it omega. Now let's call the whole region omega, the boundary of the curve as delta omega. Okay. Now what I want to understand is number of points from Z2 that are on the boundary of this convex body, on this convex curve, versus number of points that are inside this convex body. Make sense what I am saying? So when I tell you some problem like this, is it obvious why it should be connected to something like that ILP problem? Not LP, I of P comma L. ILP means something different, but okay. So, but this you can prove an estimate on this. These kind of like problems where you have to estimate number of objects lying on the boundary with number of objects lying inside. These are what are called isoperimetric kind of problems. Isoperimetric problems. Okay. So you have, I am sure you already know one thing. Okay. So let's say I give you, there is a region in R2, okay, whose whose area is unit area. Okay? Or let me frame it like this. So, there is a closed curve, non-intersecting closed curve in R2. The area it encloses is of unit area. Okay? So, what should be the minimum length on the minimum length of the curve? Do we know this object? See, there are many. So, I can make a triangle. Exactly. Unit disk is one, right? These are isoperimetric problems. You can actually prove of the many. So, that I can make a triangle, right? That will also have a unit area. I can make a triangle with a unit area triangle, right? But that does not mean that has the smallest perimeter. A disk will have the smallest perimeter with respect to the volume it encloses. This is of that form. Okay? Good. So, what we will be proving is a classic result in discrete geometry now. The theorem is called Semireddy-Trotter theorem. Theorem. This is from 1983. They proved is size of I p comma L is less than equal to p size of L whole to the power 2/3 plus p plus L. So, when I write like this, okay, this means up to a constant. There is a constant, I do not want to write. Or other option is just write this is equal to order of the whole thing. So, this is the estimate. What is the most trivial estimate that you can come up with? Every point is on every line, Mn. Right? We will see some more non-trivial estimates than that. Okay? But finally, this will be proved using properties of planar graphs and probabilistic method. Probabilistic method is something that Sandeep Sen, Rajiv will use next week. So, some flavor of that will be introduced in these lectures also. Okay, so, this is the thing we will be proving completely. Okay. This estimate does not matter if L is replaced by circles, still goes through. It goes through for slightly, there are some slightly more general bounds for general algebraic, general curves satisfying some particular properties, which includes, the family includes circles and lines, but we are saying we will stick to this to simple objects, because the main ideas is in this objects. Like once you understand the proof of this, you to some extent can reconstruct that proof also, like get those bounds. Okay. So, let us look at another problem. So, this is another one of the starting problems of discrete geometry, is what is called Eda's unit distance problem. So, this was introduced in 1946. He introduced two fundamental problems in this paper, which has been like a cornerstone problem for discrete geometry for some time now, especially incidence geometry. Okay. So, now the question here is the following. How many unit distance pairs can there be with in a set of n points in R2? So what is the problem? So if I give you n points in R2, how many unit distance pairs you can get? Any pair of point determines the distance, right? You can calculate the distance between a pair of point. So how many such pairs will you have, which are at unit distance away from each other? Make sense the problem? Yes? No? It's okay? Good. This is a very like simple sounding problem, right? I mean, this is one of the really, this has been a really hard problem for a long time. Still, many things are not known properly. Okay, not many, but like yeah, in high dimension, many things are actually still open. Okay, in R2, there is still some, we can get still some estimates, but in higher dimension, even from 3 itself, it becomes much more shaky. Okay, so in terms of trivial estimate, how many can there be? Trivial estimate? How many? All the pairs are unit distance, or any 2 points are unit distance from each other, then it should be n choose 2. Right? Okay. So what Edosh proved, this will be theorem 2, again in the same paper, I think in the same paper, yeah, I think so. So we will denote this number by un, okay. Un is the given n points, number of points you can get. Okay, so you have he put a following estimate. He proved that un is up to constant less than equal to n to the power 3 by 2, greater than equal to n to the power 1 plus c by log n. So given any n points in the plane, you will get at least, so I will write it like this, at least these many number of, up to an order constant, these many number of unit distance pairs you can get. See, you can obviously, if you take n random points, let's say in a box which is like 10 cross 10, if you take random points, how many number of unit distance pairs can you get? It will actually be 0. It's not that hard to actually prove also. So let's say the way to look at it is, so let's say the box is like 100 cross 100, let's say, I was taking n random points, okay. I inserted the first point, okay. What is the probability that the second point is unit distance away from this? It has to be on a circle, but the volume of the circle is 0 compared to the volume of the box. What is the chance of there is 1 on this circle? It's a 0 probability event, and you can just look at it. So what basically he showed, there is a point set, but the number of unit distances at least greater than this. And what he showed was, take any set of n points, any set of n points in the plane. So this inequality written like this is slightly confusing. So take any set of n points in the plane, there will be at most n to the power 3 by 2 pairs which are unit distance away from each other. Okay? Did you get the distinctions? Okay, good. Huh? So what does this side? I am just loosely writing it like this. So what does this mean? This side. What I mean by this side is, take any n points in the plane. Number of unit distances, number of pairs which are unit distance away from the length will be unit distance between these 2 points, will be at most bounded by n to the power 3 by 2 up to constant. And there exists a point set in R2 that will determine at least these many number of unit distances. Okay? So now, so what we will be seeing again in this class is, so Edosh's bound has been improved. It was improved by Semeradi. So basically it will use what is called the Semeradi order theorem, is what is called ST theorem I will call. It was improved by using ST theorem only, Spencer, so This is Joel Spencer, Semireddy, Trotter in 84 proved that un has to be less than equal to n to the power 4 by 3. Okay. This will use ST theorem. ST theorem is that Semireddy-Trotter theorem for incidences. Okay. Okay. So let's see another one. These are the 3 problems, and the other one is what is called ADAS, again in the same paper, distinct distance problem. So the question is the following, again in same paper 46. The question is minimum number of distinct distances that can be determined by n points in R2. So this is the question. He wanted an estimate in terms of n, number of points. So by the way, can you even for un, can you think of a linear bound, a point set that will have at least linear number of unit distances? Take a line and place the endpoints unit away from each other, right, like this. Like how many unit distances, how many pairs you get that are unit distance from each other? N minus 1. Okay. So order n, right? This, the other side of the bound, if you see, it's actually better than this. This is asymptotically better than that, by the way. If you look at this term, so let's look at this term one slightly closely. What it says is it is n times 2 to the power log n by log n, right? There is a constant c here. Whatever, for the time, let's say assume that the constant is 100, because something like this. This, as n tends to infinity, tends to what? Tends to infinity, right? So this is strictly stronger than linear. Constructing this point set, you have to be careful. And proving this bound is actually more. Constructing the point set may not be that hard, but proving that it is actually the growth factor is like this is a hard problem. You have to be okay. Good. This problem, the one that I have defined now, this problem has also, so it has also proved some interesting bounds here. So again, so we will denote this number by dn. Okay, dn will denote this number. So dn denotes this number. So now the question, another question. What is the trivial estimate for dn? Number of distinct distances. Again, the construction that we had, points unit away from each other. What will that give us? N minus, so if I fix this point, I will have 1, 2, 3, and finally n minus 1. And dn is the minimum among all distinct distances you can get, right? These are the 1 to n minus 1 are the distinct distances you get, 1, 2, 3, dot, or n minus 1. So dn has to be less than equal to n minus 1. So he also proved an estimate which, so let me slightly give you the construction, which is really, it uses, the construction uses a beautiful result in number theory also. Is, he said, okay, so he wanted a, so this is an upper bound, right? Upper bound, right? Dn is the minimum, so this is an upper bound. I have a state which has n minus 1. Okay, so now he says, like, can I get something slightly more better than this? So he took a grid, unit length grid. So the length of these things are 1, which is square root n cross square root n. Okay, and he got these points. So how many points do you have? N points. So we are in good shape now. Okay, and he now computed the set this distance. So like this d of p1 pi pj square, where pi pj belongs to this set S. Okay. So rather than taking the distance, I am taking square of the distance. Why am I? What is the use of taking square of a distance here? It will give me integers. It will give me integers, right? It will be some I, some j. The distance between this point and this point will be square of the distance will be I square j square. Okay. Maximum. What is the maximum value of d p I j square? N. Okay. So then you can use this famous result by Landau and Ramanujan. So it says that number of integers from 1 to n that can be represented as a sum of squares of two integers. Okay, positive integers, sum of square of two positive integers. That estimate is theta n by square root log n. This is tight, actually, the bound this cell is tight. So the trivial bound was linear in n. So if I take these n points, how many distances can I get if I use this result? See, here the distances that you are getting are between 1 to n, between the set 1 to n, and the distances, square of the distances are between 1 to n, and each of these distances will be square of some I square plus some j square. But this estimate is tell you at most these many you can have. There are at most these many numbers from 1 to n. You can represent sum of two positive integers, square of two positive integers. So how many distances can you get here? Square. See, either I can estimate number of distinct distances or number of distinct square distances, right? Same. Okay. So this will tell you. So this was a okay, so theorem. It's a good net page. So this is theorem. What was the number? Whatever. So let me write it as. Again, in the same paper, I think he proved this. He proved that then Dn is of the order n by square root log n. See, if you don't use that result, it is not obvious how to prove that bound. If I don't use that number theory result, n by square root n, n by square root log n, just as I said, constructing regular point sets, even for a regular point set, computing this how many distant distances you can get is a non-trivial result we have to use in number theory, by the way. Okay? So these may look very innocent sounding problems, okay? But to prove any interesting result here, you have to, most of the time you have to get into some deep math. Okay? So this has been there. So he conjectured, I think, also that this will be the bound. Conjectured that dn will be something like theta. Okay? So what do I mean by that? So if you take any n points in R2, okay, you should get as at least n by square root log n many distinct distances. Pardon? Okay, so let me write like this. There exists a constant for which dn will be greater than c by square root log n. Theta, you don't know theta notation in complexity algorithms? Big O, omega. So, when I said omega, is big O this notation, you know? Oh, okay, okay. So, when I say something is, so let us say some function fn is theta Tn. What do we mean by that? We mean there exists constant C1, C2 such that Fn is less than equal to C2 Tn greater than equal to C1 Tn. Okay. Up to constant, the bound, it was thought this n by square root log n will be tight. Okay. There was like huge, even like getting it something, no one was even getting close to this bound by the way, okay, for a long time. And then there in 2010 there was a breakthrough result where they really invented a new way of looking at incidence geometry problem. This is by Guth and Katz. Oh, sorry. This is called polynomial method, 2010. They showed that dn will be omega n by log n. So, if I forget about square root log n factor, they have almost closed it, okay, the bound. And to solve this, they really have to bring in really new ideas in this area of mathematics. Okay. I won't be able to cover this. This requires like at least 4 or 5 lectures to cover the whole thing. Basic idea of something like this I might introduce in the tutorial. It uses a generalization of what is called Ham-Sandwich theorem. Okay. So, let us stick to these 3 problems only, and let us go back to so, okay. So now the goal of this today and the tutorial session will be to get a proof of ST theorem. Okay. So the original proof, so what do you want to prove? Prove ST theorem. Okay. So how many of you know what is a planar graph? Okay. What do you mean when I say a graph can be drawn in a plane? How many of you know this idea? What does it mean? Rather than the two person behind. Planar graph is something not people don't know. Planar graphs. So can I draw all? So what do I mean by even a drawing a graph? That is the first thing we should look at. Okay. So what do we mean by drawing a graph? Graph is a combinatorial object. It is a relation, right? It encodes. You have a vertex set, a graph G. You have a vertex set, you have an edge set. What are edge set? Edge set is basically size 2 subsets of V. That is it, right? Yes, no? Right. So, what do we mean when I say it is a planar graph? So, what do we mean planar graph is, what you can have is, you can have vertices can be represented, the vertices V, I will say G is planar if I can represent the vertex V, vertices V by points in the plane, and if there is an edge between, let us say, vertex V1 and vertex V2, I will draw it by a curve connecting these 2 points. Ideally, you want it to be simple curves, whatever you want. I mean, like curves, you do not have to make it straight line curves also. So, what do I mean when I have planar graph? When I can draw the graph, like I can have points in the plane corresponding to the vertices of the graph, and edges will be curves connecting the dots, and no 2 curves should cross each other. Ideally, let us say there is a curve like this, I don't want self-intersecting curve also, like I don't want a curve like this. I want to reduce this intersection, self-intersection. So, why will I make a self-intersection with itself, right? Makes no sense, right? So, but you can allow to have, not allowed, you can have intersections like this. Also, if you have a vertex and two edges incident to the same vertex, okay? So, this edge and this edge, okay? You do not want them to intersect each other also. You do not want some draw the edges like this, because again it makes no sense. This intersection I can easily remove, right? Whatever be your drawing, I can remove this intersection. What will I do? Rather than using this line, I will use this. Okay, so let me. It will be something like this. The black one I removed, right? And the intersection goes down by 1. Okay. So, let us say the graphs that I can draw on the plane. So, this is what is called drawing graphs in the plane, and the graphs that I can draw on the plane such that there are no intersection between edges of the graph are called planar graphs. Is it clear what the definition of planar graph is? So, I was thinking about giving a brief idea about what is the Euler formula of planar graphs and stuff like that, but let us say forget about it. Okay, just let me directly tell you the result that I will be using for planar graphs. Okay, planar graphs has a nice property. So, by the way, can we draw trees in the plane? Everyone knows what is a tree? What is a tree? Is it a graph or a living object? What is it? Is it? Not having a cycle. Can I draw a tree in the plane? Should be, no? Kind of behaviors will tell you how to draw a tree in the plane, right? Isn't it? If I do a breadth first search. Okay, good. So, how many edges do I have in? So, if the number of vertices in the tree is n, how many edges can I have in the tree? Pardon? Good. For planar graphs also, you get some restriction on the number of edges you can have in terms of number of vertices. Okay. So, let me say, so let me now numbers these because I will be using this. This is called bound on the number of edges of a planar graph. Bound on the number of edges in planar graph. Okay. So, if the graph G is planar, if G is planar graph, then number of edges is less than 3 times the number of vertices minus 6. This is something we will be using in the proof. Okay. So, now obviously, so see the number of edges, what does it mean? The number of edges has to be linear in the number of vertices. This itself tells you there will be graphs which will, whatever way you want to draw on the plane, the edges will cross, right. For those kind of graphs, what you will try to do is reduce the number of crossings as much as possible. Okay. This introduces a notion what is called crossing number of the graph. Okay. So, let me introduce this, what is called crossing number of graph. Crossing number of graph. So, it will be denoted by CR of G. Okay. So, what do we mean by crossing number of a graph? So, again remember the rules of drawing. What did I say? Do not self intersect an edge, makes no sense, okay, because ideally you want to reduce the number of intersection between edges. Why will you intersect an edge with itself? Then you will add a crossing, right. So, you will know self intersecting edges. Any two edges, if they are incident to the same vertex. Okay, so let's say this V1, V2, V3, and you have a edge V1, V2 and V1, V3. Okay, you don't want to draw these edges in such a way that they cross each other, because if there is a crossing that is happening, you can remove that crossing. So you want to draw them like this. This is rule 1, this is rule 2. Okay. Another rule is, so what are the kind of edges that are allowed to cross, by the way now? Their vertices, each edge will have a corresponding vertex pair. 2 edges are allowed to cross if their vertex pair is disjoint, right. So this thing can happen, sorry. Okay, so this is one vertex, this is one vertex, this is one vertex, forget about this part. Okay. But I don't want these many crossings. Again, 2 edges should cross each other once only, not more than once. So why? See, these crossings, let's talk about these 2 crossings. I can reduce this crossing easily by slightly drawing this in a different way. I can go like this, and then I can follow this path, right. So I can reduce the crossing number by 1. I can keep doing it until I will be having something like this. This is perfectly fine crossing. So this is rule 3.
So here they are crossing after the midpoint.
Pardon?
Here rule 3.
Yes.
Crossing each other. Edges are crossing each other.
Yes.
Can we do cancel? Only one cross is allowed.
So there are different variants of family of graphs that can be said. So when this is there will be graphs where you will have crossing like this. You cannot avoid. Planar graph C has linear number of edges. We know there are graphs which has non-linear number of edges. No? So let's say the number of edges is n log n. Let's say whatever way you draw, you will have crossings. There is a way to estimate also how many crossing will be. That will something we will be proving. Okay. Okay. So how long can I keep doing this? So let's say you have something like this. This is one edge, the other edge is like this. So by the way, if you have something like this, you can always, if it is even like this, you can always reduce the crossing, right? If it can go like this, you will remove these 2 crossed path, right? No, but now there is no crossing, no? You can keep removing 2 at a time, but if there are odd number, you will end up with 1. Once you end up with 1, you keep reducing, and once you end up with 1, this trick you won't be able to apply anymore. So basically idea is this lens that is forming, you are bypassing this lens. How do you remove this one? No, but they, sure, but there are other edges in the graph, no? You will start crossing. I have just drawn 2 edges that are crossing. So I will give you an example and let's see whether we can remove all the crossing from that graph. So let's do one example and then it will be clear. Yes? Which one? So no. So see, what I'm saying is there is ways to reduce the number of crossings between a pair of edges. Okay, but you can make it go down to. You can either make it completely go, or you can make it down to 1. But
still we will say that it is not.
What do you say? If you can draw without crossing, a graph will be planar.
But if it is not possible,
then whatever reduction you do, you will still end up with some kind of crossings. See, when we were reducing the crossings, let's say something like this is happening.
some kind
N vertices touching each other is not crossing. Crossing means interior of the curve that you are drawing. There is what we define the crossing. So, like this is not a crossing. Let's say you have two edges emanating from 1, 2 and 3. This is not a crossing. This is a vertex, this is a vertex, this is a vertex, and there are two edges. Not touching. These are crossing means it is incident to this. It's clear what I am saying or not?
If we follow this crossing, then the point which we are starting with gets lost.
How is it getting lost? The point you cannot throw away the points. No? If you want to remove, let's say I can remove these two via this. So what I do is I go from here, here, and like I go here. Then I can reduce this crossing. But I reduce it by 2. I may still be end up with one more. Like 1 will stay. Initially it was 3, it goes down to 1.
So is it okay if I start my...
There are 100 ways of drawing. I cannot keep drawing the graphs, but what I am trying to say is if there are more than one crossing of an edge, you can make it go down to 1 and not create new crossing in this process. Okay? So, the basic rule is a pair of edges can cross once, a pair of edges incident to a vertex, you are not allowed to cross the way you draw it. These are the rules you have. One edge should not self cross each other, so you should not draw it like this. And there is a third one. The third one is, let's say you have 3 edges, they should not cross at the same point. One point, these 3 edges are crossing, right? Any pair of them are crossing, but they should not, 3 or more edges should not cross at a point. And this is you can again remove by a small thing like this. Again, this is a technicality, it does not matter. There are ways to define crossing number of a graph, which again I have still not defined, but there are ways to define crossing number of graph where number of edges can cross at the same point. Okay? But for this, just work with the current framework. So, this is rule 4. So, the way you are supposed to draw the graph is with these rules. Okay? Now, you define what is the crossing number of the graph. Crossing number of a graph is the graph drawn on the plane. For a G is drawing the graph on the plane such that you will exactly have CRG many crossings of edges, okay? And you cannot draw it with CRG minus 1 many crossings. Then the crossing number of graph is called CRG. Okay? So, this is how you define CRG. You can draw the graph with CRG many crossing in the plane, and you cannot do it with CRG minus 1. It's the minimum way. Okay? So, let us now try to estimate this object. Okay, so what is the time? Okay, I still have time. Okay. Okay, so let us use a loose crossing bound. So, what you can prove is number of crossings is greater than equal to number of edges minus number of vertices plus 6. So, remember a planar graph has how many number of edges at most? 3v minus 6. So, this is basically minus of 3v minus 6. Pardon? Yeah, this is for general. No? So, let us say v is equal to 2. Will there be a crossing in that graph? You do not have to look at your pages, just if v is equal to 2, can there be a crossing? No, I am saying, so you can put, so let us say if v is equal to 2, how many edges can you have? Or 0. So, let us say 1 minus how much? Minus 6 plus 6. Okay, good. So, you have it should be greater than equal to 1. But for a graph where is crossing with there are 2 vertices, can there be a crossing? So, okay, I am not writing, but it has to be like you have to assume it is greater than equal to 3 or something. Even for 3 you do not need it, greater than equal to, you should start looking at it from greater than equal to 4, greater than 4 actually. K4, a complete graph on 4 vertices you can draw in the plane, right. So, but this minor I am not. So, but this estimate, is it okay? Pardon? K4 is not planar? I am not sure, let me see. I do not work in graph theory, but I think this is K4, no? It's planar. What about K5? K5 is not planar. From what theorem this is? Do you know? Kuratowski's theorem, right? K4 is? This is, isn't this the K4 on 4 vertices? You have a square, and if I draw this diagonal like this, is there a problem? I am not drawing it with straight lines, no? Curves. Even for straight lines, there are ways to do it, but okay. I mean, you can do it like this. What about K5? So, K5, can you draw? So, you can so what one thing, so Kuratowski's theorem tells you what, or minor theorem for planar graphs. So, if your graph has a minor, forget about minor, if a graph has a K5 in it or a K33 in it, okay, you cannot draw it in the plane. It tells you something more even stronger, okay. But for surely for a graph that has a K5 in it or a K33 in it, you won't be able to draw it in a plane, okay, right, without crossing. Good. But K5, so it has to be greater than equal to 1. So, this will be an exercise, show that crossing number of K5 is 1. Okay, this is a question. Okay. Okay, so let us try to prove this, whether we can get some kind of an estimate for this. Crossing number is 0, exactly. So, I mean, crossing number is defined, it is for, I mean, normally you define it over a family. So, you say family of graphs with crossing number k. Planar is family of graphs with crossing number 0. It's okay. So, let us do it in the following way. So, let us say I have drawn the graph, you have a graph G with vertex set and edge set, okay, and I have drawn it in the plane in such a way that it has exactly CRG many crossings, exactly, okay, and I know since the crossing number is CRG, I should be able to draw it with these many crossings, okay. There exists a drawing with these many crossings, okay. So what I do is, let E prime subset of E be a maximal set of edges that does not cross in the drawing. Okay, maximal. So, what do I mean by that? In this set, if I include one more edge from E, I will intersect some edges from E prime, the way it is currently drawn in the plane. Okay, it's clear. So, now let us say I look at the graph G with the same vertex set, but edge set E prime. It is a planar graph, right? What should it satisfy? What will be the size of E prime? Okay. Now, look at the edges in complement of E prime. Look at edges in E minus E prime. My claim is each edge from E minus E prime will contribute, will intersect at least one edge from E prime by construction. Why? Because E1 was the E prime was the maximal set of edges, subsets of E that were not crossing, right. It will contribute 1. If somehow, so each of the edges here will contribute a crossing. So, CR of G is greater than equal to size of E minus E prime, has to be, right. Each edge may cross even more, not just one, it may contribute even more, but at least one every edge from E minus E prime will contribute, right. If I can find a lower bound for this, I am done. But what is the size of E prime? Size of E prime is basically size of E plus E minus E prime. Sorry. Size of E is size of E prime plus. In this equation, just replace E prime with size of E prime with size of E minus E minus E prime. This just replace here. What do we get? Can you check? What do we get? If I replace here, I get E minus E prime to be less than equal to 3 times V minus 6. I bring both of these terms on this side, this term I bring it here. So, what do I get? So, let me just remove this equation and just write it here directly. I do not go to a new page. So, what do we get? We will get E minus E prime is greater than equal to size of E minus 3V plus 6, but I know the number of crossings is greater than this. So, this completes the proof. So, as an exercise, think of another way of proving this result. Okay? So, just see, you should always try to find different proofs of the same results. You will understand the tools used in the proof better. Okay? So, one way you can try to understand is, so see, there was a drawing in the plane of a graph, okay, with of G like this, right, with the minimum number of crossings. Right? One other approach, so these were the crossing points, right. This was one crossing, this is one, this is one. So this is a G, drawing G. Convert G to a graph H in the following way. Make these crossings to be the vertices. So the vertex set of H will be these crossed points plus the original vertices of G. This will be a planar graph. What will be the degree of the vertices of the cross point? What will be the degree of a one cross point? It has become a vertex right now, right? 4. Use this. result. So, in G is a planar graph. So, you can use the planar graph result here. What will be the number of vertices in G? Is the original number of vertices in H, is the number of vertices in G plus the number of crossings that you have. So, let me write like this. There is and what will be the number of edges? The number of edges in H will be the number of edges you had plus the force, but that has to be this edge that is incident to here is always double counted, right? It will be counted here, it will be counted here. Okay. Same idea as sum of the degree of the vertices is order the number of edges, 3 times the number of edges. How many number of edges? Twice the number of edges. Using the same idea, we can prove that this will have these many edges. But this graph is planar, use that planar equation, you will again get back the inequality that we proved. Okay. So, I end here and I will do the crossing lumba in the next one. So, what we will do now? So, just using property of planar graphs, I can bound the number of crossings a graph can have. This is linear in the number of edges, right? So, what did we prove? This CR of G is greater than equal to, so I keep forgetting this, minus 3V plus 6. See, this planar equation is actually follows from what is called Euler formula for planar graphs. So, it uses some topology of plane and drawing graphs on the plane enforces this condition. Okay. But that gives you a linear bound in the number of edges. Okay. The tight bound will use this topological property of planar graphs plus probabilistic method, and that we will do in next class. Okay. So, why are we doing crossing numbers? Using crossing numbers, we will be able to prove ST theorem, similarity to order theorem using crossing numbers. So, the main idea, the main result that we will be proving, if your number of edges in your graph is greater than equal to 4 times the number of vertices, okay, the number of crossings will be at least omega of cube of the number of edges by square of the number of vertices. And up to a constant you can have a matching, any graph you can draw with these number of crossings. Okay. But the optimal one finding is hard question. I think it is NP hard. Is NP hard, right? Yeah. And not NP complete. Given a drawing, you can obviously think, but then given a drawing has to be done in. For what is the property of NP class? The certificate should be what? Can it be some irrational algebraic curve? So, it has to be a proper curve that has nice representation. Okay. So, straight line, let us say. If you restrict it to the straight line also, you will get similar. So, see, this bound is for any drawing. So, this bound holds even if you are doing a straight line drawing, right. Up to a constant there is an algorithm to generate this, but it is in NP. So, if you give me, you restrict yourself to straight line drawing, okay, then the certificate itself is the line, like these are the edges that I am connecting. So, only thing you have to give is what? Given a graph, only thing you have to tell me, I know what are the edges, you only have to tell me where you place the vertices, but then also you have to be careful. Why do you have to be careful? Let us say I can draw the graph with straight lines, straight line drawing I can do, but the one that minimizes uses irrational coordinates. But you don't have, so you can work around this problem, you can make it rational and there are ways to do it. Okay. But straight line there is a way, but you have to restrict the class of curves you are allowed to join, you are allowed to make edges with. So, straight line one you can get a tight estimate like this, and for that you can have a algorithm and stuff like that. So, like for planar graph, if you give me a planar graph, I can basically draw it on a grid of order n cross order n size. So, give me any planar graph, you tell me the graph is planar, okay, but you say I do not know how to draw it. That is a very natural question, right. I know the graph is planar, but can you tell me how to draw the graph? You can draw it in polynomial time on a grid of order, I mean they are extremely tight estimates, I think something like 2n minus 1 cross 3n minus 1 or something like this grid. I mean this constants I do not remember, but it is very tight estimates you can give, and they are polynomial time you can do. But when it comes to crossing, these are all NP-hard, NP-complete problems, even for specific class of curves you are using. That's it. Thank you.